Good morning, everybody. All right, so we're going to finish out this section today and probably introduce a little bit of substitution and elimination. And then Friday, of course, the test will be posted, but we're going to still have class and I'll still deal with the next section. So, but it won't be on the exam. The only thing on the exam will be organometallics and I believe conversion of alcohol to alkyl halides.
Dr. Russell, I have a quick question.
Go ahead.
So for our homework, we turn our homework in the day that the exam opens or the day that the exam closes?
You can do either one.
Okay.
It doesn't matter.
Okay.
But it can be, you know, I think the syllabus says you got until the day after the test or something like that. But yeah, you can do either one. It doesn't matter. Okay,
thank you.
Yeah. But if we're finished with a worksheet and on something else, we want to submit it early, by all means do it. All right, we're going to go ahead and stop. I think we already finished all these problems, except for one that I wanted to do. And it would be this one. Well, you know what? We're going to go ahead and begin the substitution and elimination because I think we finished all the problems here that I wanted to finish with. Actually, I want to try it. I'm going to cut this out.
Cut it.
We're going to work this one, and then we'll start substitution and elimination. All right, so this problem is going to require a couple of steps. We're going to have to do a retrosynthesis to get to the immediate precursor of the product. So we have to break this down and by working backwards. There's one step in here that the problem indicates, and it says, provide the reagents necessary to carry out the multi-step synthesis below. So this is the key to the question right here, that it's a multi-step synthesis. It happens over multiple steps. And it says, hint, one of your steps will involve hydroboration oxidation, right? Using BH3 and hydrogen peroxide. So that particular step, what do we, let me think of how to phrase this. We talked about this before in a previous section. What are those reagents used for? Anybody remember? All right, so the hydroboration oxidation, I'm just going to abbreviate it. We use that to convert alkenes into alcohols, right? We talked about this when we were doing what we're doing, stereochemistry and reactions, I think. We talked about that. So we started out And this is our start material. This is all they gave us, right? Cyclohexyl iodide. That's all they gave us. So we want to take that, and you can see right here in the product. Let's think about how to break this thing apart. So let me draw it out. And when you do, again, a retro synthesis of a molecule like this, what you're looking for is ways to break it apart. Right? You look for places that you can break bonds to see how to put it back together. So you can see here that there's a bond right here between the cyclohexane ring and this chain over here. Right, so if we were to break that bond, the immediate precursor to that would be something like this. Right, when we go back to that start material, plus something like that, right? Where X is some functional group, some leaving group, or something like that. So when we think about it, we know what we started with this. So we need to figure out where we got this from. All right. And so it tells us that one of our reagents is, or one of our reactions is a hydroboration, right? So if we take that alcohol, we can think in terms of hydroboration. Where did it come from? Well, the alcohol had to come from an alkene, right? Because we have the information that hydroboration / oxidation is one of the steps in the process. So there had to be an alkene involved somewhere, because hydroboration, that's what it works on alkenes to turn them into alcohols. All right. So now let's think about where this came from. All right. If you wanted to take, and this is all based on stuff we've already talked about. If you wanted to take this and make a new, you can see right here, there's a carbon-carbon bond right here. So if you wanted to take the alkene highlighted in green, I'm sorry, in red, and make a carbon-carbon bond with this molecule, what's one way you could do that? Right, it's a way we've already talked about. Actually, two ways that you can do it.
This is the retrosynthesis part, right?
Yeah, we're just working backwards, but we're trying to figure out how we can put these two pieces together.
The purple and the red?
Yes.
Okay.
What methods could we use that we have discussed to put those two together? Right, we're not going to touch the iodide. We're leaving that because they gave us that as a start material. But how could you couple those two?
Like the organometallics?
We can use one of our organometallic methods, right? We studied two in detail. One of them was what?
The Grignard.
Grignard, and what's the other one?
Gilman.
So if I wanted to take that alkene and make it into a let me backtrack. How could I make this into a gradient, right? How could I, what would I have to do to make X be magnesium from an alkene?
Dr. Russell, I'm confused.
Go ahead. What's your question?
I'm okay. So we went from I'm just confused. So we went from the retrosynthesis to the hydrobromation oxidation.
We're still doing the retrosynthesis. What we're saying is that the hydroboration is going to be one of the steps is going to involve hydroboration oxidation, right?
Okay.
And that step, we know is going to have to involve some type of alkene because hydroboration oxidation works on alkenes. It turns alkenes into
alcohols.
Mm-hmm.
Okay.
So if we look at the overall molecule, we chopped it right here. You see where we chopped it, where the red bond is?
Yeah.
Mm-hmm. So those are my two fragments that I will get from that.
Okay.
So now my alcohol, again, if I'm doing hydroboration as one of the steps, that had to come from an alkene.
Mm-hmm.
Right? So that's what I have highlighted in red.
Okay.
Right, so we're working backwards back to the original starting material. Now the question is, that alkene right there that I have shown, what would I start with for X to be magnesium or to make that into a gradient?
Wouldn't you have
Go ahead.
So wouldn't you have to like you would have to add magnesium to it to make it like
Yes.
I
could start with this, couldn't I?
Yeah.
I could start with a vinyl iodide and then add magnesium to it at low temperature and make this into a granule. Is that right?
Yes.
Right. So I'm gonna go ahead and put the iodide in. All right. Is that rain too loud?
No.
No.
All right. Let me know if it gets too loud. I'll move inside. Okay. So now we have all our pieces. We can think about how to put these two things together to get that product that we have shown up here. All right. So I don't want to start with the granule. I actually want to start with this right here. But I want to show that we made the granule. Then I want to show how we coupled it in the second step. And then the third step, how we turned the alkene into alcohol. So we did this. I'm gonna write it out linear first. So we start with this. Right, and we start with this. Treat it with magnesium at -78. What am I going to get from that?
The gradient.
Mm-hmm. I'm going to get this out. Am I right? MgI. Yes.
Yes.
Then I'm going to take that and react it with the iodide that they gave us. What am I going to get?
The pieces gonna come together.
Yeah. We're going to couple them. Is that right? So I'm going to end up with this. Here, Yes or no?
Yes.
And then if I take that and then I treat it under hydroboration conditions, which is to do BH3, and then in the second phase of the reaction, do hydrogen peroxide and sodium hydroxide. Remember, this is going to put an alcohol on the least substituted carbon of that alkene, because it's anti-Markovnikov. So that would give me this. All right, and that's the end of that synthesis. But we had to work backwards. We had a product, we had to work backwards to see what the actual two starting materials were. So if I wrote this as a multi-step synthesis, I would write it like this. So I would say here is my iodide, but you can write it both ways. And then over my arrow, the first step will be magnesium. And then at minus 78 degrees Celsius, second step would be to add in the cyclohexyliodide, and then the third step would be to do the hydroboration. So that's how you would write it out, and I'll go ahead and copy that. And that's how you would write that out. You know, it's still a multi-step synthesis, whether you write it out in a linear form or whether you write it like this. But that's another way that you could express it, right? But all we did was look at this product, found places in the product where we know we could cleave that, break that product apart, and then use a known reaction to put those pieces back together. So that's how you have a giant molecule like Taxol, like some other molecule that we talked about already, right? You know, when you make something like that, you don't just go in and start doing reactions. You look at it and you look at places where you can break bonds and fragment it into pieces, right? Because there are two types of synthesis that you can do. You could do convergent synthesis, which is what this is an example of. Right, and that is, you know, merging fragments together. So you synthesize fragments separately and then merge them together. Right, and then you can do also what's called linear synthesis. Right, and that's where you just start with one single starting material and you keep building on it until you reach your final product. Right. So for this section on organometallics, we're going to stop with that, and then I'm going to introduce you to the substitution and elimination section. There is an entire like handout package for that. So what I'll do, since I didn't download it and you don't have it, I'm just going to give you a brief introduction into substitution and elimination, and then we'll start with the handout on Friday.
Can you scroll up really fast, please?
Let me switch to a, and I'll upload this. It won't be right after class though, because I gotta get ready for lab this afternoon, but it'll be today. So let me start a new set of notes. All right, so now we're going to move into all right, so again, we're still talking under the umbrella of synthesis and application of alkyl halides. So one of the uses or applications of alkyl halides is to use them in substitution reactions, right? Use them as substrates for substitution reactions, right? So we know now one of the applications is to use them in coupling reactions with organometallics. Another is to use them as substrates for substitution, because the halogen on the alkyl halide is a good leaving group, right? So in both substitution and elimination, right? You have a what we call a substrate. That's your starting material. Right, both involve a leaving group. Hold up 1 second. All right, so both have a substrate or a start material. Within that substrate, that's where your leaving group is. So both have the substrate must have a leaving group. Both types of reactions, substitution and elimination, are dependent on conditions. And by conditions, I mean like the type of solvent, the type of nucleophile or base, and the type of substrate, right? Whether it's a tertiary or a secondary or primary substrate. So both substitution and elimination are condition dependent. They have a leaving group involved in the substrate, and they both have to start with some type of substrate. So the most simple type of substitution right? We talked about this a couple of times. So with substitution, we're going to talk about Sn2 and Sn1. So Sn2 substitution, when it happens, normally it's going to happen on a primary substrate. So this is my leaving group. need to put that up here too. All right, so it's also dependent on the leaving group ability and that's specific to Sn2 and E2. All right, so for Sn2, this is my leaving group. I'm going to react it with some nucleophile. And then my product, the nucleophile, is going to replace the leaving group. Right? That's a basic Sn2 type substitution. And we've seen that already when we did alcohols to alkyl halides. Right? And then for Sn1, this is not going to happen on a primary. This is normally going to happen on a tertiary substrate. I'm reacting this with a nucleophile, and the nucleophile is going to substitute for the leaving group. Right? And the leaving group normally leaves with a pair of electrons. So it's homo or heterolytic bond cleavage for that leaving group, right? So for E1 and E2, those are elimination pathways. Again, the E2, it can happen on a secondary or tertiary substrate or primary, but it prefers tertiary. We're going to talk all about that on Friday, but it prefers tertiary because of the substitution pattern of the double bond that you get after the elimination. All right, but for this, I'm just going to write out
For the Sn2 and the Sn1, was it the Sn2 that's like concerted in the Sn1 stepwise?
Yes. We're gonna talk about all of that. So the Sn1 is stepwise, where you lose the leaving group first, you get a carbocation intermediate, and then the nucleophile comes in and attacks. But right now, I'm just showing the outcome. But you're 100% correct. Sn2 is concerted, and then Sn1 is stepwise. So Sn2 and E2 are both considered what we consider concerted reactions, right? The difference is, instead of a nucleophile, you use a base. You have to have a base present for E2. And there is a thin line between what's a nucleophile and what's a base. And, you know, the differences between them are very nuanced. It's a very nuanced distinction between what we call a Bronsted base or something that acts as a Lewis base. So we'll talk more about that later, because there is a way to distinguish between whether something is a better base than it is a nucleophile or vice versa. So we'll talk about it later. All right, so this is an example of an E2. One of the things about eliminations, we learned this in part 1. All eliminations result in the formation of pi bonds. Anytime you do an elimination, you're going to get a pi bond as one of your products, or pi bond in the product. So it'll be that plus, I'm going to write this out and we'll talk about the mechanism later. H base plus the leaving group. Right, so in E2 elimination, the proton that's adjacent to your leaving group, we call it an alpha proton. That proton is going to get ripped off by the base. And we'll talk about the mechanisms also. Right, so this alpha proton is going to get removed by the base, and you end up with a pi bond, you lose your leaving group, and the base does proton transfer with the substrate. E1, totally different. You don't need a base. The base is generated internally, either from your leaving group or from your solvent. You can actually do the E1 reaction in protic or aprotic solvents. And we're going to talk about all of that, what that means. I think we've already discussed it a little bit when we were looking at, I forget what section we were in. We already kind of touched it a little. So with E1, let's start here. Let's go back to this tertiary substrate. So you'll end up with a pi. It's still an elimination. So you're going to end up with a pi bond in the product plus your leaving group. Right? And again, with E1, the leaving group can actually act as the base. So you'll have sometimes you'll have a competition between the leaving group acting as the base or the solvent. If the solvent is involved in any kind of way, the conjugate base of the solvent acting as the base. So we're going to talk about that. So with elimination, the result of that process is a pi bond in your product. With substitution, what you're doing is exactly that. You're swapping out your leaving group for a nucleophile. You can see the difference over here, right? Both types of substitution, Sn2 as well as Sn1. Any questions about anything we talked about so far? All right. So one of the other parts of substitution that we're going to see and I think we talked about this already too. So this is just a review. Right, what we see if you have let's say you have a molecule like this. We're going to say that iodine is our leaving group. You know, OH is a horrible leaving group. So iodine is going to be our leaving group. Sorry about that. And we're going to react this with this sulfur nucleophile. Right. And the fact that, and I'm gonna set the conditions so that we know that it is so we'll know it's Sn2. Right. So, and I think we talked about this in one of our alcohol to alkyl halide problems, but we're going to review it, refresh it here because you're going to see it a lot. So when I do this reaction, what happens in this case is you do get an Sn2 substitution, but right, you get a Sn2 substitution, But you'll notice the stereochemistry is different, right? Anybody remember what we call that when the stereochemistry changes like that?
Are you talking about diastereomers?
Say again.
Diastereomers?
I'm not. I couldn't really. Did you say inversion?
I'll put it in the chat. I can't. My mic is messed up.
Okay. All right. So if it's Sn2, one of the key characteristics is what we call inversion of stereochemistry, right? And the reason for that is because of the approach of your nucleophile. This is a concerted reaction. And if I were to draw that stereocenter, so I'm gonna just kind of abbreviate the ring without having to draw it out. So this carbon in the ring right here, I'm just going to show it here, right? So the iodine is here. Right, and so when the nucleophile comes in to kick out the iodide, remember it's not going to come from the same side because of sterics, and so it's going to come in from the opposite side. So it's going to attack from here. Right, so that's going to attack here, like so. And then by the same token, the carbon iodine bond is going to be broken like so, right? So the approach of the nucleophile is always going to come opposite of where your leaving group is due to sterics. So that's why if your leaving group is on a chiral center, that's why you see inversion, because of the approach of the nucleophile. All right, so you're always going to see that inversion with, if it's Sn2, you'll see inversion. If it's Sn1, which can also happen, you're going to see what racemization. All right, so if it's Sn1, you're going to see. I'm going to add a methyl group right here. To make that carbon tertiary, right? So when this happens, it's stepwise, and so you're going to lose iodine first. So you're going to end up with a tertiary carbocation. Right, this OH is still here, but now with this intermediate, Your nucleophile, let me show you that. I'm gonna draw it out with planer. Right, that sulfur, let me move this down some, can come in, because that plus that carbocation is basically it's just an empty p orbital. So you got a plus charge here, right? But sulfur can now attack from either side of that p orbital. Either it can hit either lobe of the p orbital. Right, so it can come here, or it can come from the bottom side. Like it's at either side. Let me put my OH back in. Right, so the fact that that nucleophile can attack either face of that p orbital, that means that there's no, you're going to get two products. It'll be a racemic product. So then your product ends up looking like this, where you have here, and then so that's one product, but you're also going to get the other product as well. Right, and depending on how much influence that OH group has on the outcome, which probably be very little because of where it's positioned. No, it should be over here. Sorry, let me fix that. Depending on how much influence that OH has, that's gonna do. That's right. That'll count. It may bias the outcome and make one of those stereoisomers more prevalent than the other, but the size of OH is not that great, and there's nothing really to cause it to create like a huge steric bias based on where it is. So more than likely you'll get a 50-50 mixture. All right, so we got to stop here. We'll pick this up on Friday. Go ahead and when you get a chance, go ahead and download that handout from Blackboard. It's in the assignments folder, and it's a folder that is just labeled substitution. So it's like one package. Just go ahead and download it, and we're going to work through that for the next. It might take us a week to finish it, and then we'll move on to another topic. All right. So with that said, are there any questions? And if not, we're going to go ahead and stop here, because I want to keep pushing and then get to something and not be able to finish it because I only got like 30 seconds left. So we'll stop here, and then we'll pick up on Friday where we left off.
Thank you.
All right, y'all have a good day. I'll upload all this stuff. It'll be later this afternoon. It won't be right away because I got to drive up for lab. So, but you'll see the video and you'll see the notes and all that stuff. I'll send an announcement after I put it up.
See you later.
All right, y'all take care.
Thank you. Have a good day.
You too.